The secret of your success lies in the power of choice. Silicon, silicon carbide, and gallium nitride power semiconductors come with very unique characteristics, offering different benefits. To provide the highest level of system performance in your application, you have to know what each of these technologies can bring to your designs. Silicon, silicon carbide, and gallium nitride, when to use them. Gallium nitride is a technology of choice at fast-switching frequencies, providing the highest efficiency and power density at an overall optimized system cost for power-hungry applications. Wide bandgap materials complement silicon solutions, pushing the envelope of power efficiency, size, and weight reduction further for even higher levels of performance and enabling new topologies. Silicon carbide can withstand high temperatures and harsh environments. In addition, the possibility to use standard drivers with it makes silicon carbide an easy-to-use option for improved performance compared to silicon. Choosing legacy silicon provides you with the best price-performance ratio. This mature technology addresses a large variety of use cases in which price performance is desired. We know that the choice is not easy, but as your trusted partner with our several decades of experience in power semiconductors, Infineon, the expert in all three power technologies, is there to help you. We are also a committed and well-positioned supplier to fully support your growth at the highest quality standards. Our ramp-up capability, as well as 300mm wafer fab for power semiconductors and continuous R&D investments in next-generation wide bandgap and silicon technologies, together with our technology know-how, is all there for your success. Choose from our broad power portfolio of high-quality, highly efficient, and ease-of-use products. Visit our website to learn more about wide bandgap technologies.
And thanks, Professor Nguyen, inviting me to this presentation. The topic that I'm planning to cover today is to introduce an affordable simulation platform for industrial power systems. Okay, next slide. So this is the outline that I will cover today. First of all, I will have a brief introduction of the hierarchical control of the industrial power systems currently in industry. Then I will introduce the HIR setup, hardware in loop setup to test the industrial controllers. Then I will explain what is the motivation of the work in this presentation. Then I will present my proposed model, and I will show the results and also the conclusions. Okay, so this is a very typical, very simplified one-line diagram of industrial power system. So basically, you have one incomer, then you have on-site generation, then you have transformers, then you feed the loads, right? Then for each of the important breakers, usually you may install some kind of the IEDs, the intelligent electronic devices, right? Such as relays, PLCs, and also the IO modules, right? To monitor the breaker status, to monitor the health of the breaker, and also to measure the analog signals of the breakers, like the active reactive power, voltage, frequency, right? Then also the IDs will control the breakers, either the protections, right, or the local controls such as the ATS, the transfer scheme, or it may have wide area control, which sends the controls to the local local relay, then controls the breakers, right? Then also for the distributed generations, you also have local controllers. For example, for this generator, it has a exciter to control the voltage. Also have governor to control the torque or the speed, right? Then for each of the generator, there may be another layer of the generation controller to coordinate the exciter and the governor control. So those are the local control device level controls. Then there may be a wide area controls for the entire plants. So here I list some like a typical structure of the wide area control. So first, you may have a data concentrator to connect all the data from the distributed IEDs, right? Then this data concentrator also will get the control commands from the controller, the centralized power system controller, and pass the control commands to the IEDs, right? Then you have the power system controller, which is like the brain of the wide area control. So it gets all the measurements from the data concentrator, and also make the calculations, make the logic, run the logics to make the decisions about how to control the system so that the system can be reliable, right? And also it has one HMI for the operator to change the settings, to issue commands, to monitor the system. So this is a typical hierarchical control of the industrial power system right now widely used in industry. Okay, so from the previous slides, we can see there are different layers of the controls, right? One is the device level, which is the IED controls, right? So for example, the breaker control, and also the DER control, and also maybe ATS, the transformer auto taps. So those are the device level control. Then we also have the wide area control. So it's more sophisticated, right? For example, we may have the load shedding system, right? So if we have a plant, it has on-site generation, and you know, when there is a bad day, the utility is lost, right? You may lose the power import from the utility, right? Then if your generation is not large enough, you may want to shed some loads so that your generation can feed the critical loads. So in that case, you will need the load shedding system. Also, there could be generation shedding system. So I used to work in a site in Saudi. So for that site, the on-site total generation capacity is like 4 gigawatts. Okay, but the total load is 800 megawatts. Okay, so if it lost utility, then it shouldn't shed the load, but it should shed the generation because it has a 3.2 gigawatt surplus generation, right? So then in that case, you may want the generator shedding system. Okay, then there is also generator control system. When you are when it is utility connected, you want the generator control system to dispatch the generators so that they are used evenly, right? Or proportionally to their capacity. But when it's islanded, then your generation system will maintain the system frequency and voltage, right? And also there may be tie line control system. Like you want to you have contracts with your utility. Based on the contracts, then you need to specify what is the tie line flows, what is the amount of power you can import from the utility, right? Or what is the amount of power you can export to the utility. And when the utility is lost, you may also need an auto synchronization system, right? So when you are disconnected from the utility, then you need this system to synchronize your system back to the utility. And also you will need the decoupling system, which is used when the utility is lost. You need this system to detect the loss of the utility and isolate your system so that your system can be, can run in islanded mode. So these are some typical wide area controls that are widely used in the current industrial system. So because there are so many wide area controls, so there is a time coordination of these controls, right? So for example, for the critical contingency, then you need a very fast controls, right? For example, if you lost the utility, and when you are import power from the utility and you lost the utility, based on the status of the PCC breaker, you may want to implement contingency-based load shedding system, right? So upon the event happens, you detect the loss of the utility. You calculate the amount of the power shortage, right? Then you need to make the decision very fast to shed your non-critical loads, right? So that you can maintain the system frequency as quick as possible. So for this kind of the critical controls, it happens very fast, usually smaller than 100 milliseconds. Basically, you have communication time, which is about 10 milliseconds. Then the controller time, controller calculating time is like 2 milliseconds. Then the breaker opening time, which takes the majority of the time, about 50 milliseconds. So totally around 100 milliseconds, you need to share the loads. You need to detect the loss of the opening of the breaker and then share the loads. Okay. Also, the decoupling scheme needs to be very fast, because if the utility is lost and you don't decouple with the utility quick enough, then the utility will drag your system down to blackout, right? So there are usually a decoupling scheme implemented in the PCC breaker, which monitors the frequency or voltage of the utility, right? Then when it hits, it triggers your decoupling schemes. Then the scheme will open in the PCC breaker to isolate your system from the utility. There are also some backup wide area controls, right? Which is not as fast as the one I just introduced. So the backup one is like, for example, if your PCC breaker is open, however, if there is an alarm in the breaker, okay, you may not detect the opening of the breaker, right? So in that case, the breaker is opened, but you didn't receive the signal of the breaker open, right? So your control system, your fast control system, contingency-based load shedding system will not detect this event, right? So in order to save your system, you can implement the backup system, which monitors the frequency of the system. Because if that breaker is open and you lost the power supply from the utility, your system frequency will goes down, right? Then this backup system, you monitor the frequency of your plants. Then when the frequency goes down to a certain level, it hits your under frequency triggers, then you can shed load automatically. So that's the backup system. And also there's a slow control system, such as the generation control. It doesn't need to be quick, because some of the large gas turbines, even you send, usually it controls like each time you send parts to raise it or lose it, it's like 20 seconds you send one, then it can respond slowly, right? There's a large time delay in that. So there's no meaning to send it very fast. And also the synchronization system, you don't need to make it very fast, because when you synchronize to the grid, that means your system is already healthy, grid is healthy. It doesn't matter you synchronize in 1 second or 10 seconds, right? Because both systems are healthy. Then the talent control system is also something that is very slow, because when you have a contract with the utility, and usually the power system dispatch controls are very slow. So even you may have some load increase, which makes your tie lines, import more, but you don't need milliseconds or seconds to correct it. It takes time. You can take time to correct that tie line flows. Okay. And also overloading system is also something, some controls that is slow. So the overloading system works in, for example, if the load increases and your generator is overloading, but it doesn't trigger the under frequency, and there's no breaker opens, so there's no contingency. So in that case, the overloading system will detect the overloading of your generators and trigger some non-critical loads to reduce the loading of your generation. Okay, so this is a time coordinate. Yeah,
Niannian?
Sure.
So you say that there is the remedial action occur after the frequency reaches pick up values. So typically, what the value of frequency that can trigger the remedial action here?
This I think you won't like the answer, but the answer is it varies. Okay. So usually when usually the frequency, the pickup value of the under frequency, we need to do a under frequency study. So the way we do this study is we model your power plants, right? Then we model your system in a simulation platform, right? So for example, the RTDS. Now today I propose a new affordable form. You can also simulate it there. Okay. So we simulate your system, then we need to do some coordination, right? So for example, you don't want your frequency very high, because if your under frequency very high, remember that there's a primary load shedding system, which is the contingency-based load shedding system, right? So if the event happens, contingency-based load shedding system detected and opening the breaker, right? During that short time, you haven't trip your load yet. The frequency will go down, right? So you don't want your under frequency triggers higher than the deep of that contingency-based load shedding system. Otherwise, your contingency-based load shedding system triggers, then it also hits your under frequency. You triggers it again. So you double shed, right? Then you will hit the over frequency. So you need to make sure that your under frequency, you need to do the study for various scenarios to detect the deep of your contingency-based load shedding system. And your under frequency load shedding system should be lower than your lowest contingency-based load shedding system frequency. Okay, you need to set it lower than that one, because that is the primary load shedding system, right? At the same time, you can't make it very low, because there is a protection of the generators, right? So usually the generator protection maybe at in US is like 54 hertz, right? So you don't want to set your frequency too low, right? For the easiest example is you cannot set it at 54 hertz, right? Because if you set it at 54 hertz, it hits 54 hertz, you share the load, but at the same time the generator triggers. So you can't save the system, right? Because if the generator trips, the system blackout, right? So you need to set it high, and not just higher than this one, because remember, when your under frequency triggers, right? It triggers, but it doesn't mean the load is shed, because once it triggers, it sends the trigger signal to the controller. Then the controller sends the trip signal to the load. The load breaker has time to open, right? So for this delays, your frequency continues goes down, right? So you need to make sure that when the under frequency triggers, you have a margin there. The frequency goes down because of all these delays, and then the load breaker opens, load actual triggers. Then the frequency comes back. You need to sure that deep don't trigger your generation protection, right? Because if it triggers your generation protection and opens your breaker, then the game is over. So there are coordinations there. It's not a one value fits for all the system, right? So there is a study there. I can't give you a one value for that one.
Okay,
Does that make sense?
Yeah.
Okay.
That answers the question.
Okay. So usually when we deploy the wide area controllers, we need to test it in-house. So what is the reason to test it in-house instead of testing it in the field, right? So there are 4 reasons I listed here. One is when you test it in the field, you need to plan the outage, right? Which sometimes is very costly and not possible. For example, I give you one example. I did a project for one oil field in Saudi. It's Saudi again, but a different site. So that site every day it produces 1 million barrel of oils, right? So consider the current price of the oils is like more than $100 per barrel, right? So it produces 1 million per day. So that means if you plan outage for 1 day, that will cost them $100 million, right? So they won't let you do this test in the field because to do the entire controller for them, it costs you maybe $2-3 million, right? To build this controller for them. But now you want to test this controller 1 day is $100 million. That doesn't make sense, right? So that's the reason, for most of the sites, I have to say, the customer don't want you to test it in their site. They want you to test it before deploying to them, right? That's the reason we need to test it in-house. Second, the second reason is because the misoperation of the controller could result in tremendous loss and even the human safety. So I also give you an example. So that is not a project that I directly involved. So that project was developed before I joined my previous company. Then but it runs for several years. Then one day, some bad, multiple bad things happens. Then the system blackout. Okay, it's not just our controller fault. It also has a protection faults, several units faults plus our controller faults. The system blackouts. Then my previous company like have 5,000 engineers. I never met CEO, but on that day, the CEO comes to my desk, shaking my hands and says, please work hard to find the root cause, because the daily loss of that blackout is $50 million per day. So that night, the CEO said, please don't go home, find the root cause, then go home. So you can see how important our work is, the electrical power system work is, because if the system misfunction, then it could reduce huge loss, and also, or even the death of humans. So it's very important. That's why we need to test the controller very extensively in-house. Then the third reason we need to test it in-house is because is that in the in-house environment is less stress. Okay, if you test it in the site, it's very stressful. I had that experience. The customer, stands beside you when you are testing everything. He watches you. He asks you questions. At that time, you cannot think, because all the stress comes to you. If anything misfunction, then it's your brain is blank. And also test in-house, you can test different scenarios, right? So for example, you can put a fault at any location in-house in the simulation platform, but on-site you can't test any faults, right? Sometimes. And also you can change the load profiles very easily. You can disconnect from utility. You can reconnect from utility. All of that very easily. So it's more efficient, more easy for to more extensively to test your controllers. And also, if you find bugs in your controllers, when it's tested in-house and you find that bug is easy to fix, because you don't have stress. And also you have support from your R&D, from your colleagues, you can ask questions. But on-site, if you find a bug, you are on your own. Some locations, there's no phone signals, there's no Wi-Fi, you can't ask for anyone. You have to use your experience to figure it out. And you have to figure it out because the customer is standing beside you. And if you don't figure it out, he won't be happy. This figure shows a typical diagram for the hardware in loop testing. So you can see the devices in the blue circle in the blue area. It's the field devices, right? It's the actual equipment, actual settings that you will deploy to the site. Okay, so that's the devices you need to test, right? Then the red one, the one inside the red area is the lab devices, right? So the interface between them are the same between the white between the one in the field and also the lab. So the interface is the same. Therefore, when you test it in the lab, the field device from the field devices point of view is actually the same as tested in the field, because all the interface is the same. It gets all the measurements. It sends the control signals. Then it sees the field response of the control signals. So everything is the same from the controller point of view. That's how you should set it up in the hardware in loop environment. Okay. So the way to set it up is first you have a simulation platform which runs all the power system calculations. It can be dynamic calculation or the steady state calculation, like the power flow calculations, right? Then this calculation values will feed to a protocol converter, right? The reason to have the protocol converter is because you need to have this interface the same as the field, right? So if you directly only have the power system simulation platform, the interface won't be the same. So you need sort of protocol converter to convert the values provided by the simulation platform to the same protocol used in the field. That's the reason you need the protocol converter. Okay. Now the motivation of the work. So today I'm proposing a affordable simulation platform for to test the power system controllers, because you know, in the current system, in the current industrial systems, I know some of the vendors they don't have hardware in loop testing. They may have open loop testing. So in the hardware in loop testing environment, I think there are two popular vendors. One is the RTDS, one is the OpenRT. So I'm not very familiar with OpenRT. I'm more familiar with RTDS, which I used a lot. So the RTDS equipment is actually very expensive. Like for example, for the latest version, like the Nova Core, right? If you buy one chassis of Nova Core and it has 10 core license, okay, so the total devices cost you maybe 600K to 800K US dollars, right? So I mean the full licensed one. But the customer, you know, usually when we do this testing, so because as vendors we can use the RTDS extensively, right? Because we have projects coming all the time. That's why we buy it. But the customers, once they finish the project, they may not buy it, right? So what they can do is they come to our side to do the testing. After the testing, they leave. Then they have no chance to test this system anymore. So some of the customers wants to have a simulation platform on their site so that they can test some scenarios they can use for their operator training. They can you know they can do maintenance rehearsal, or they can, if there is an event on site, they can do some post-event analysis, right? So that's why they need the simulation platform. But the RTDS is very expensive. They couldn't afford it. That's the motivation why we need to provide an affordable simulation platform for the customers. So and also the testing using RTDS is also very costly. So when the vendor, you know, when the customer went to a vendor to test using RTDS, it cost about 5K to 10K per day. So it's not a cheap test. So this is a new hardware in loop tester setup that I propose. The field devices are similar, right? Because the field devices we need to deploy in field. Then for the lab devices, now you see the simulation, the power system simulation, instead of a individual power system simulation, I move it inside the protocol converter. I don't know if you can see the text here. It's hidden on my side, but this is the protocol converter. Okay. Then the power system. Okay. The power system simulation, I move it inside the protocol converter because I want to use the protocol converter, which is usually an industrial PLC, right? It converts. It has data comes in, then it converts the protocol, then have data comes out. It also has some PLC programming capability that you can run some logics. So basically, I am in this presentation, I'm proposing a computational friendly model, which you can run that model in your PLC inside the protocol converter to run the power system simulations, right? And then feed the data to the field devices. Okay. So now all you need is just one PLC, industrial PLC, which costs about $4,000. Then you can have the protocol converter. You can have which supports various protocols. So you can provide the signal using the same protocol as the field. At the same time, you can use the same device, the PLC logics, to calculate your power system response. Okay. So there are some evolutions of the power system simulation platform. The first version, when I joined the company, I call it a dummy version because there's no calculations behind. All the power flows are entered manually. Okay, so maybe you can't believe that that there's such dummy version there. But when I joined that company, it's that version. Then after 1 year, there's another engineer who developed the DC version. So basically now it has DC power flow calculations. It can provide the active and reactive power. Okay, but sorry, it can provide the active power and also it can provide the active power only. Yeah. And then the reactive power and voltage needs to be entered manually. Then there's an AC version. In my previous company, actually we skipped the AC version because we directly jump to the UPF version, which is the version that I will present today. Okay, so I the AC power flow is very popular. I mean, it's the theory of AC power flow is well developed and is presented in every textbook, right? But there are some shortcomings of the traditional AC power flow model. One is
Niannian,
yes.
I think I interrupt. You may need to speed up a little bit.
Okay, I will speed up. Sure.
Okay.
So there are some shortcomings of the AC power flow model. First is it needs a slack bus, right? Everyone probably knows that. Then when you calculate the power flow, there's no frequency because it assumes that the frequency is always nominal frequency. Then the active power generation is always constant when you calculate the traditional AC power flow, right? And also the reactive power is always either it's always the voltage model, right? When you calculate the traditional AC power flow, you always assume if there's a generator, the voltage of the generator bus is always constant, right? If the generator hits the maximum or minimum, then you convert the PV bus to PQ bus, right? However, in the industrial power system, then there are some special requirements. For example, because in industrial system there's not enough generations, right? You usually have several distributed generations. So this generator, this DGs has very limited capacity. So they can't be as strong as the utility to always hold at a nominal frequency. And also it couldn't act as the slack bus, right? Because it has a limited capacity. And also the DGs usually have its control mode. It is not usually operated in constant power. It has like a Droop mode, ISOC mode, right? So those needs to be considered. And also the reactive power of the DGs also have several modes. It's not just the voltage mode. Okay, so now we will enter the model development. So for this is a model in every textbook for the traditional AC power flow. Basically, you have the power injection. Then the power injection into a bus will be equal to all the flows through each branches, right? So this is how this equation describes. Now, when we consider the DGs has different modes. It has an ISOC mode. So in this mode, the DG will maintain the system frequency at a nominal, and unless the DG hits minimum or maximum power, then it won't be able to maintain the frequency. And there's another mode for the DG is the Droop mode. Basically, if the DG produce more power, if the frequency of the system drops, then the DG will produce more power. If the frequency of the system increases, the DG will automatically produce less power to compensate for the system power loss or surplus. Then there's another one which is what used in the traditional power flow, which is the constant power mode. Basically, the DG's power won't change regardless of the system frequency. Okay. So for the ISOC mode, this is the same curve. So basically, the DG wants to maintain the system frequency, right? So it will provide the support, whatever support to maintain the frequency. So if the system has surplus power, which is the total load plus the loss minus all the generation, which is the power imbalance, right? So those imbalance will be distributed among all the ISOC units. So this is the equation for the ISOC mode DGs. Okay, so the unbalanced power in the system will be distributed among all the ISOC units, as long as the unit is not hitting the maximum or minimum. Then for the Droop control, this is the equation to describe this curve. Basically, If the frequency change, the power will change. Okay. Then the third equation for the constant power is very simple. It's just maintain the constant. So for the exciter, it also has it has 4 modes. One is called, the DG has 4 modes. One is called the voltage mode. Basically, the DG will provide whatever reactive power it can provide to maintain the terminal voltage. Then the voltage droop mode is similar to the frequency droop mode. Basically, if the terminal voltage changes, the DG reactive power output will change according to the droop line. Then the third mode, the third or the fourth mode is called the constant Q mode or the power factor mode. Basically, the DG will provide the constant Q in regardless of the voltage. Okay. So for voltage mode, the equation is to maintain the voltage. Then for the voltage droop mode, this is the equation which describes this line, right? Then for the constant power mode or the power factor mode, this is the reactive power produced by the DG. Okay. And also in distributed, and also the load has a frequency and a voltage dependency. So when the frequency and the voltage are deviated from nominal, the load value will fluctuate. So this equation describes the load frequency and voltage dependency. The P load IN is the load value at a nominal voltage and nominal frequency. Okay, so when the voltage and frequency change, there's a fluctuation on the loads. And similar to the reactive power, when the voltage and frequency change, the reactive power of the load will change. Okay, so now when we look at the power flow model, this is the ISOC mode bus. So basically, the ISOC generation, the power produced by the ISOC generation will also be influenced by the unbalanced power in the system with the distributed factors. Then for the Droop one, the Droop power produced by the Droop generators will be determined by the frequency of the system. Okay. Then for the constant power, it's a constant, right? So to combine these 3 equations, we get a universal equation like this. This is the power reference of the DGs. Then this is the load frequency and voltage dependency. Then this one describes the control modes, right? So if it's a ISOC mode, this X is the PS, okay? This beta is the alpha, the distributed value. If it's a Droop mode, then this X is the frequency, and this beta is a derivative of this equation, okay? Then for the reactive power, it has 4 modes. Then for the voltage mode, this is the equation, and this is a traditional power flow equation, right? Then for the voltage droop mode, this is the equation. Basically, the change of the voltage will impact the reactive power generation of the voltage droop bus, voltage droop DGs. And then for the constant power DGs, then this is the equation, and then we can combine these three equations into a universal equation. Okay, so here shows the simulation results. So this model is being modeled in the MATLAB and using the IEEE 30 bus system as the testbed. Okay, and so this is the system inputs. Basically, in this IEEE 30 bus system, it has 6 generators. So these are the power reference, voltage reference, Pmax, Pmin, Qmax, Qmin of the generators, and also the Droop. Okay, so we can see a few scenarios. So this test is test between our model as well as the RTDS results. Okay. So the first scenario we'll test is the off-nominal frequency at a grid connected mode. So this assumes if the grid is running at a off-nominal frequency, for example, in this test, it runs at 60.3 hertz, right? Then we can see the simulation results between the proposed model and the RTDS. We can see the error is very, very small, right? Then this is the bus voltage results. The error is also very, very, very small. Then, yes, anyone is speaking?
One.
Okay.
Skip, continue. No problem.
Okay, then the second scenario is testing the air-landed case with a few DGs, but the DG has some of the DG hit the P limits. Okay, so this is the modification of the inputs, so that some DGs will hit the maximum or minimum, right? So after the calculation, the system frequency will settle down at 59.92 hertz. So this couldn't be done in the traditional power flow because the traditional power flow couldn't calculate the frequency. And this is a comparison between the UPF and the RTDS, and you can see the result is very, very good. And this shows the bus voltage difference between the RTDS and the proposed model. The difference is also very small. The third scenario is testing the airland system with all the DGs performing in Droop mode. Okay, so some of the modification to the inputs so that the frequency has some deviation, and eventually the frequency calculation is 60.16 hertz. Okay, so basically in steady state the frequency will settle down at 60.16 hertz. Then this is the simulation results, and again it's the error is very, very, very minimal. This is the bus voltage results. Then the next scenario is all the DGs runs in Droop mode, but some of the DGs has hit the maximum limits. Okay, so all these scenarios are very practical in the real situation. So again, some modification for the inputs so that some DGs can hit the maximum, and eventually the system settles down at 59.67 hertz. And this is the results. Again, the error is very, very, very minimal. Then the fifth test case is the total system generation capacity is not enough. Question? Okay.
So is it your oh, sorry.
Okay, so the total system generation is not enough. In this scenario, again, some inputs are modified, and eventually the frequency settles down to 58.36 hertz, right? Then this is the simulation result. So I just want to spend 1 or 2 minutes here. So in the traditional AC power flow, actually you cannot calculate this scenario because if you have a generation shortage in the traditional AC power flow, your system still will converge, and all the shortage power will be provided by the slack bus, right? Because slack bus will provide everything for the power flows. So that's why you won't see the frequency decay, and you won't have realistic results. So in this proposed model, it can see it can identify the shortage of the generation capacity, and then it can calculate the frequency dips because of the shortage of the generation. And this shows the results. The results is very close to the RTDS results. The bus voltage is also very close. Then the test 6 is tested the power factor mode. The power factor are set to be 0.9, and this is the results. It's very close. Then the 7th one is tested the voltage Droop mode. Again, the result is very close. So here is, by the way, so this affordable simulation platform has been commercialized, and right now it has been used in many projects in US and Saudi. Yeah, and right now it's a very popular product for the customers because it's very affordable and the result is very close, and they can own the product. They can test in their own facility. They can, they can train their operators. They can use this device to train their operators. Then they can do the maintenance schedule. So this is the schedule conclusion. So in this presentation, we propose a model for an affordable simulation platform. And also we explained that why the hardware in loop testing is very critical. Yeah, and the simulation result is very good. Yeah. Okay, we can come to the question. Yeah.
Niannian, I
Yes.
heard that you said that DC can provide some reactive power. Is that correct?
No, that's not correct. DC couldn't provide reactive power.
It actually consume, right? Some of them actually consume reactive power.
Oh, you mean DG? Oh, sorry, I heard it wrong. Sorry, I saw you say DC power flow. DG?
No.
You are talking about
Generation.
distributed generator. Okay. So sorry, I saw you are talking about the DC power flow. So what's your question about DG?
So you say that it can control the reactive power.
Yes, it can control the reactive power.
But I heard that like because of too much DC, we kind of some of them like a wind farm, they consume reactive power. Is it correct?
So the DGs are a lot. It depends on what you are talking about, right? So because the DG, this term means a lot. Actually, all the generations in the power plants, you can call it a DG. It can be conventional gas turbine generators. It can be steam generators. It can be wind turbines. It can be PVs, or it can be batteries, right? So
yeah, I want to ask about specific about wind farm.
For the wind farm, actually, I don't have experience. I never work in any projects for the wind farms. I know I never have a wind farm experience. I know I have experience for PV, battery, gas turbine, steam turbine, but never wind farm. So okay. I don't have a firm answer for you.
Okay, thank you. Okay. Anyone else have a question for Dr. Cai? You can raise your hand on this the menu of the Zoom, or you can type the question on the chat.
So I just have a very general question. So is this simulation consider the power system protection in the system if there's some if there's some fault happen, like do you simulate that case when we have fault in the system in power?
So right now this simulation is like the very customized one, right? So in this presentation, the model I propose is a very general model. It depends on how you want to implement this model. If you implement the protection algorithms in addition to this model, then it provides the protection, right? So what I mean is that right now the one proposed in this presentation is like a foundation, right? This foundation tells you if you use this model, then you can calculate this. But if you want to do protection, that's like an application, right? So for example, protection control, that's an application. So it can do that, but it needs you to implement it. For example, the one we used for our application is the wide area controls, right? So we use this mathematical model to calculate the power flow, the power system status, right? Then we feed the status to the controller. Then the controller makes the control decision and send the control commands back to this model. So this is kind of like the closed loop testing. So for the protection is similar. So you have protection devices. Then you have this power system model to calculate the power system states. So when you can simulate a fault inside this model, then the stator, the force will be captured, be detected by the protection devices. Then the protection devices will send the trip back to the model to open in the associated breakers. So that's how we do the simulation.
I see. Thank you. Yeah.
Yes, I see. Amia is raised his hands.
Yep.
Yeah. Hello, Niannian, and
Hi.
it's very good to see you here. I haven't seen you in a while.
Yeah.
Yeah. So my question is, do you see in the United States that there is a market for reactive power trading, meaning that the traditional
Reactive power
way
load
of
shedding?
yes, for example, there is now discussion on electric vehicle or using generally power electronic for the ability to inject reactive power to the grid or absorb reactive power, and they can do that very fast. But my question is there any market or need for rapid reactive power systems like this?
Yes, it does. It does. Actually, you ask the right person. Okay. So reactive power load shedding is a very difficult problem. Okay. So I used to attend a conference. There's a guy from GE who is presenting the reactive power load shedding, but the way he described it is not working. I know it's not working, although he explains it, because this problem actually is very hard. Our group has spent maybe 15 years to working on this problem, and you ask the right person because recently I worked with another engineer, and we have a solution for this. It has not been commercialized yet, but regarding the marketing part of the reactive power load shedding, yes, there's a need. I have worked in one of the Brazil projects. Okay, so for that project, they have 3 generators, but they have a huge reactive power import from the utility. If one of their generator is in maintenance and the utility is lost, then their system will collapse because of the reactive power shortage. Okay, so when I did the project for them back in 2015, they have requested us to provide the reactive power load shedding, but we don't have that techniques at that time. Then later on in 2018, we have another project with Chevron. Okay, so the way their system is, they have contract with the utility, but the utility only bears them for the active power, but not the reactive power. Okay, that's why when they run their system, they have very minimum active power import because the active power will cost them money. But they will import a large reactive power because it's free. So they will max out all their generations to produce the active power, but not produce any reactive power. All the reactive power will come from the utility. And if the utility is lost, they won't have active power loss, but they will have huge reactive power loss, and their system will collapse because of that. Okay, so because of they have that problem, and it happens one time their system collapse, then they reach out to us and ask us to provide the reactive power load shedding, and that's the initiatives for us to do to start this research again because we started many times, but it's very difficult, so we stopped many times. Then in 2017, 2018, we started it again, and eventually we come with a solution. Yeah, but there is a marketing. I don't. The marketing is not very big because most of the customers will request the active power load shedding, but there are some who request the reactive power load shedding, and yeah.
And do you see resident load points? I heard that there is discussion on applying a charge for reactive power consumption as well. Because right now, let's say residence utility in the United States, they only charge based on the active power consumption. For industrial application, they charge them based on active and reactive power. But now there's discussion that even for residential to charge the cost of their active power as well, but it's not regulated yet.
Yeah, that is possible. But, I have seen some utility bills for industrial system. I didn't see they charge significantly for the reactive power. Maybe it's changing, but in the previous years, I didn't see they have reactive power charge significantly. It's a very cheap reactive power.
Yeah.
It's close to
Yeah.
free. Yeah.
Yeah. Thank you very much.
Now, actually, Niannian doesn't care because he moved to Google already.
Yeah. No. Yeah.
Mình muốn bảo với các bạn
Okay.
thính giả ở đây là các bạn sinh viên, nếu mà các bạn ngại đặt câu hỏi bằng tiếng Anh thì các bạn có thể đặt câu hỏi bằng tiếng Việt, sau đó bọn mình có thể translate. Thế mọi người có câu hỏi gì không ạ? Nếu mà không có ai có câu hỏi gì thì mình sẽ để cho bạn Niannian rời leave the room. Niannian, thank you for your presentation. I know that it's 12 a.m. at your time, right?
Hello, may I have a question?
Oh, yes. Please go ahead.
Hello.
Yes, I can hear you. Yeah.
Okay.
Go ahead.
This is Wen from Hanoi University of Science and Technology. From the flyer of this webinar, I think you are working for Google, right? I think
Yes.
Google is an IT company, right?
Yes.
But your field is power system. So can you share something about Google, about what kind of what you are doing in Google, or what kind of field of interest in Google, and kind of job opportunity for students like that? Thank you very much.
Yes. Yeah. Google is an IT company. So right now the Google, Google Cloud is expanding rapidly, right? Like the Amazon Cloud, Google Cloud, Microsoft Cloud. So for all those clouds, they need to build large data centers, right? Like the large data centers with with a lot of servers, right? So for Google, it has hundreds of the data centers worldwide, and all those data centers are very load consuming. So for each of the data center, it may have loads like from 20 megawatt to 100 megawatts, and Google has hundreds of it. So you can see how much electricity Google is consuming. That's the reason Google has demands for the power system engineers to. There are two kinds of the engineers Google needs. One is the power system operations engineers who operates the Google data center power system, because it has a it is a very large load center. Then there is also research and development power system engineers who will design the architecture of the Google data center power system, the switch gears, the controls, the protections, basically everything related to power system, the designs. So Google has a group, an R&D group of the power system to do this job, and I am in the R&D group. Does that answer your question?
Thank you very much.
Okay.